I'm Phil Guertin again. I'm on the faculty at the U of A, and in this presentation, I am going to talk about some of the spatial analysis processes that we perform within AGWA, as well as some of the decisions that we made in terms of the characterization, what we do to characterize a watershed. All right, and so it's going to be a little bit on GIS, and it's also going to be about hydrologic modeling and some of the things you need to be concerned about or be aware that we're doing in the background. Right. Next slide. So basically, we are using a hydrologic erosion model, all right, Kinross or SWAT, within the AGWA framework. And the AGWA framework is really a GIS framework. And a hydrologic model is a synthesizer. Okay, it allows us to integrate a set of information: land use, land cover, topography, soils, management practices. All right, and we can then predict, okay, what is happening, all right, okay, within the watershed itself. What is the response? What is the response hydrologically? What is the response, okay, from an erosion point of view or water quality point of view? I use it for water quality work as well, all right? So a model, you know, allows us to go into an area, even if we don't have a precipitation record, essentially a weather station in the area, or a gauging station with stream flow. But we can characterize that watershed, all right, and predict how the characteristics of the landscape would influence response, runoff and erosion response. Okay, next slide. Now, this is a classification of hydrologic models, and we're on the left side, okay? Our models are deterministic. They're not stochastic, okay? For a given input set, you will always get the same results, the same output. This is really good for planning purposes, okay? This is really good for looking at cause and effect. You don't want a stochastic process in the background giving you different results based on statistical properties. Okay, you want to say, here's my watershed condition before and after a treatment or a disturbance. Okay, and we're basically just changing the input and getting the output for that characterization, that watershed, essentially representation. The models that we use are physically based models. Okay, we have tried to represent the physical processes: interception, infiltration, overland flow. Okay, Kinross is a fundamental. It's based on fundamental laws. Okay, we have an equation for each one of the processes that we're trying to model. SWAT is more of a hybrid model, but it still has individual functions for different processes. Okay, unlike Kinross, where we model infiltration using a form of green amp, okay, the hybrid model uses the curve number. The SWAT model uses the curve number approach. Okay, not as strong in terms of its physical properties, physical representation, but still, we have a functionality describing that process. Both Kinross and SWAT are distributed models. And what that means is that we can go to a watershed and we'll characterize that watershed using different modeling elements. In Kinneros, that modeling element can be conceptualized as a hill slope plane, whereas with SWAT, it's a sub-watershed to the larger watershed that you're modeling. And we have essentially these areas, hill slopes and sub-watersheds, that are connected by a channel system. So we basically are modeling water from the upper part of the watershed down. We're routing it down to the outlet of the watershed. Okay, and that's a distributed model. And again, our representation is either sub-watershed, okay, in SWAT, or sub-element, or you can think of that as hill slope, plane, okay, in Kinneros. Okay, this does allow us to, again, go into an area and we, have inputs that we are required: land use, land cover, topography or DEM, digital elevation model, soil data, and we can characterize that watershed, and we can model the response based on these physical laws, our understanding of the hydrologic process. We do not have to calibrate the model. Now that comes with a cost. We have greater uncertainty, but we do feel that we can show you relative change related to the changes in the watershed before and after urbanization, before and after grazing, before and after a fire. Okay, so that's how or before and after a best management practice is implemented. So this is how we use these tools with or without calibration. Calibration increases your certainty or decreases your uncertainty in terms of your modeling results. But we can apply these tools in an ungauged situation. Next slide. I'd like to stress again, Shay just went through this. Our primary layers include topography. We're dealing with a digital elevation model, land use, land cover, soils. And land use, land cover, okay, is really the one that we typically modify to reflect management or changing conditions or disturbance. Okay, so topography and soils are relatively constant, but the land use, land cover is a more dynamic component. And we can deal with different resolutions. We can essentially live with a 90 by 90 meter DEM or 30 by 30 meter, 10 by 10, okay, or we can deal with LiDAR data down to a centimeter scale. All right, same thing with land use, land cover, or soils. We can use different resolutions within our modeling tool. But again, this allows us to look at complex watershed responses. Okay, we are integrating this information, the topography, the land use, land cover, the soils, okay, on our modeling elements. So we come up with a unique set of input parameters for each one of our modeling elements. And I'll go through that more later on in this presentation. Next slide. All right. Now, I'm going to go through a few GIS-based tools that we use in AGWA. You can do this on your own, okay? They're in the hydrology toolkit under the spatial analyst tools, okay? And one is called flow direction. And what this tool does is it uses topography and it answers the question, what direction would water flow out of that cell? So it can flow in 8 directions: east, southeast, south, and so on. Okay, and we're going to define what direction that actually would move. And so we're actually looking at the Walnut Gulch experimental watershed here. And you can see that part of the watershed drains south. It has red colors, and part of the water the dominant flow path is north. Okay, and you can tell that right down the middle there, you can see that would be your primary channel right through there. All right, and so this tool really looks at maximum drop to determine the direction that you would actually flow in. Now, we then can take that output, the flow direction, next slide, Shay, and we now can look at flow accumulation. This tells us how many cells flowed into a downhill cell. All right, and so we're actually adding area. How much area has flown into this cell conceptually? So we're now looking at flow direction, okay, and how water is moving through the watershed. And you can see that some of the cells have 0. Those are the cells at the outer edge of the watershed out essentially boundary. And then we have 3 and 8 and 15 and 18. We're accumulating cells. Now, one of the things that we do is that we see a cell with a high accumulation value, we can assume that, okay, that may be an area where we would find a drainage channel. So, next slide. So what we can actually do is that we, go through this process. We have a DEM, we have a flow direction, we have a flow accumulation, and then we can reclassify the flow accumulation, okay, raster to define the location of the drainage channels. So the drainage channels are being defined by the DEM. We're not pulling it out of another layer, okay, from the USGS or looking at it from imagery. We are defining our flow network essentially using the DEM by reclassifying the flow accumulation raster that we've created. Next slide. So now we have some of the information that we need to start breaking the watershed up into our modeling elements. This example is really looking at what we would do for Kinneros. And so I have a given watershed, okay? I use the information I just collected to break that watershed up into channels, all right? Okay, we do that by taking the flow accumulation and reclassifying it. And so I have, a 0 order basin, okay, or the upland basin, that essentially where that essentially channel starts conceptually. It's at the outlet of those basins. And then I have 2 laterals that flow into the channel. And we take that information and we then characterize these essentially channels as straight lines. That's the length of the channel. Okay. And then we also characterize the width essentially and the length of our modeling elements, these lateral channels or the upland channel. So the upland channel flows into the head of the essentially channel. And then we actually flow into essentially laterally into the channel from the hill slope elements, essentially about this, essentially on either side of the channel. I might add, Kinneros is physically modeling flow down each one of these modeling elements. Those are the green boxes. And we are also modeling flow down the channel. We have simulation nodes placed down the channel. So we're actually adding water as we move down the channel. All right. Okay. So this is what is being put into the parameterization file that we're creating. Okay, we have these model elements. They're going to be numbered. They flow into a channel that's numbered, and we're tracking the water through the system to the outlet. Okay, so we have these rectangular overland flow plains in Kinneros that flow water into the channel elements. Now I'm going to go through how we define the model parameters for these model elements, okay, the overland flow plains as well as the channels later on in this presentation. Next. There are 4 ways to characterize a watershed. All right. threshold based, or using an existing stream network, or we actually put in points where we're going to initiate the channel, where the channel will start. Okay, threshold is the most common one that we use. We can either use contributing source area. How much upland area do you need in order to initiate a channel? Okay, that can be the percent of a watershed, or it can be a physical area, like how many acres or how many hectares. Flow length, okay, is where we actually determine what is the maximum length the hill slope can be. Okay, this is really important for erosion modeling. You don't want your hill slope to be 2 kilometers long. That doesn't make sense from a hill slope erosion model point of view. Okay, so we may want to maintain the hill slope to be less than or equal to 100 meters. That would be an example. Okay, so contributing area is kind of, but it's essentially top-down approach, and the flow direction is essentially bottom-up approach conceptually. Now, existing stream network, all right, that is where, okay, we take line work from NHD, the National Hydrologic Data Set. We identified essentially the endpoint for the channels, and that would be the beginning of our channels conceptually. But we still define the channels using a DEM. And occasionally we insert where we want a channel to start. And a good example when we may want to do this is when we have very small stock ponds in the upper part of the watershed, and we want to model from those stock ponds. So we may want to say that stock pond will be the start of our channel network. Next slide. Now, the resolution, the level of complexity that you describe a watershed will have an impact on your response, hydrologic response or erosional response. And so here are 4 examples. Here's where the contributing source area was 2.5% or 5%, 10%, 20% of the watershed. And you can see we have very different levels of complexity. With a 2.5, we have 44 watershed elements, okay? And we have 29 individual channel elements, okay? As we go down to the 20% case, where essentially the modeling elements conceptually represent 20% of, okay, the watershed, we have 9 watershed elements, 5 channel elements. Okay, so you're going to essentially a high degree of representation. You have smaller elements, okay, going to really big elements. Okay, so again, different levels of complexity. Next slide. All right. And so I'm just going to go through a few slides just so you can see. Okay, for example, here's an example of a watershed. This is in the Sierras, where the CSA was 1%. Okay, I had a stream length of over 100 miles. The average element size was 1.32 square miles. Okay, goes to the next one. Here is another case where it's only, now it's 2.5. And my stream length is 71, okay, essentially miles, okay, and basically each element is much bigger, okay, it's 3.8 square miles in size, okay. Now this does have an impact on the type of response that you may have, okay, how you characterize the watershed, what kind of complexity are you essentially going to use has an impact on response, what type of output you will get for essentially given simulation. Okay, the smaller the modeling element, the greater the channel length. That's one given that you're going to have. Okay, Now, if you have ephemeral channels like we have in Arizona, where we basically see infiltration into the bottom of the channel as water is being routed down the channel, we will see a decrease in runoff because we have more channel length, all right, because of the high transmission losses. But if you have a perennial stream and you're basically adding base water to essentially the channel as you flow down, you'll see an increase in runoff. Okay, you have more channels, okay, you have more efficient routing. This will result in a higher peak flow. It will also result in higher sediment yield related to channel erosion. Okay. More spatial variability if you have small modeling elements. Okay, you're weighted averaging a smaller area. We're more likely to retain the impact of rare types. All right. Okay, so there's some essentially advantages of doing this because you can actually represent, that rock outcropping if it's there. Okay, this does also mean that you're going to have longer processing times. So if you're really interested in peak flows, if you're really interested in sediment transport within a system, then you have to be really careful, or you really want to represent the true channel length. If you're interested in just, annual average discharge, maybe you can live with a less complex representation of a watershed. All right. So again, what is your question? What are you interested in? Also dictates how much complexity you want to use to represent the watershed. Okay, next slide. Now, each one of these model elements, be it subwatersheds or the hill slope plains, the overland flow plains that we have in Kinross, we assume it's homogeneous within that area. So we may have several different soil types overload essentially with several different land use land cover types within a given area. We will come up with an estimate of what the response would be, or what would be the input parameters given that complexity. We'll only have one set of input parameters for each one of our modeling elements. Okay, so the hydrologic parameters are an intersection of topography, cover, and soils. Okay, the bigger the model element, we're losing information. All right, so we do have these scaling issues. And we use a weighted average, okay, to essentially come up with a parameter set for each one of our modeling elements. Next slide. So in this example, I'm using the curve number to estimate how much runoff I would get for each one of these essentially modeling elements, okay, for a 1-inch rainstorm. And this modeling element had 2 curve numbers, okay, within it based on soil, land use, land cover. One was 60, that would be like a rangeland with basically a B-type soil, decent cover, okay, and 95, which would be like a parking lot. Now, I have 4 situations, 4 ways I could characterize that modeling element. I could take the arithmetic average of these 2 numbers. That would give me a curve number of 77. The higher the curve number, the more responsive the element would be. Okay, so 100 would mean essentially all the rainfall would come off as runoff. Okay, a curve number of 100. CN, okay, is a weighted value, okay, of these 2. Okay, the 60 represented 75% of the area, the 95 represented 25% of the area. All right, then I have majority rule, or I use the maximum value. And you can see very different runoff amounts using this technique, going from 0.05 with the arithmetic average to 0.002 inches of runoff with a weighted average. The majority was 0. Okay, the maximum was 0.563 inches. So again, how you come up with the input set, how you integrate the information to come up with one input set for a modeling element is critical. And we use the weighted average. I'm not saying that's the best method, okay, but that is actually what we would use. This is something to keep in mind. You may want to make sure that you have an individual modeling element for your urban areas, for example, with that high curve number. But then you're going to have to live with the higher processing cost. Next slide. All right. This is just going through the Walnut Gulch experimental watershed. We live in Arizona. A lot of our runoff is the product of convective rainstorms, thunderstorms. The Walnut Gulch experimental watershed is one of the most highly instrumented watersheds in the world because we really wanted to understand the effect of short duration, high intensity, small extent rain events, what impact did it have on runoff response and erosional response? Okay, so Walnut Gulch currently has 88 rain gauges. We also have 96 gauge watersheds, 8 of them with sediment. So we can understand the impact of spatial scale on rainfall runoff response. Next slide. All right. One of the things that we have to deal with, and this is true in a lot of systems, not just an arid, semi-arid system that we're dealing with, is that, you know, our runoff to precipitation ratio is relatively small. Okay. We get on average 350 millimeters of rain per year. Most of that water is infiltrated and then evaporated back to the atmosphere. Only 2 millimeters come off as runoff. Okay. And so, you know, we can have a pretty big impact. There can be a pretty big impact, okay, related to air associated with measuring rainfall. This can create large uncertainties in our estimates of runoff. Okay. A typical rain gauge measurement error is 3 millimeters. Okay. Essentially, wind-induced gauge error is somewhere on the order of 5 to 25%. Okay, so we can actually have pretty significant errors in terms of estimating rainfall amount, which can then lead to errors in our ability to predict runoff response. Next slide. Okay, so, you know, again, in essentially arid and semi-arid regions, runoff and erosion ratios are small. And so, you know, we're between a rock and a hard place because we are really not capturing the true amount of rainfall. So we're not going to be able to really estimate the actual runoff amount. Okay. And what we have actually found, especially for small events, we do a relatively poor job compared to, okay, relatively large events. Next slide. This is a study that we did near Walnut Gulch. This is in Sierra Vista in southeastern Arizona. We have 2 watersheds. One was a grassland, the other one was an urban area. And you can see the black line in the graph is accumulative precipitation. We also have accumulative urban runoff as well as accumulative grassland runoff. Okay, and you can see that we have a very low runoff to rainfall ratio for the grasslands compared to the urban area. All right, we actually saw, you know, 27-fold increase in runoff due to the urbanization in this situation. Next slide. And this is work that Dave Goodrich did with a student, essentially Jeff Kennedy, and we're really looking at uncertainty related to this low runoff rainfall ratio. And it's not just based on the amount of rainfall, but it's also based on these different types of watershed. We had essentially higher runoff ratio, higher runoff rainfall ratio for the urban watersheds, and we had higher levels of certainty or less uncertainty compared to the grasslands. And the gray areas are areas of uncertainty related to rainfall. Now, Dave's going to talk more about this afternoon, but we see the same results when we're looking at post-fire. Our model does a better job post-fire than pre-fire, all right? And that kind of makes sense. If you're dealing with a forested system, you can have a pretty good rainstorm event and you can still see hardly any runoff at all, okay? You know, before the fire, but after the fire, okay, you'll have a really high response. And our model actually does better under those situations. We have less uncertainty in those situations compared to essentially the undisturbed case. Next slide. Next. All right. Shay talked a little bit about this. In most cases, we don't have, okay, a rain gauge to use, especially in wildland situations. So we use data from NOAA, design storms. We use rainfall distribution curves from the Soil Conservation Service, okay, to represent an event. These curves I'm looking at are for 24 hours, but we can make that a shorter duration if you essentially if you want, okay? In this case, we're looking at 4 types, okay, of rainfall distribution. Okay, this is a design event. Okay, luckily, most of the United States is a type 2, okay, which essentially includes Arizona and Colorado and New Mexico, etc. Okay, you have slightly different distribution types on the coast. Okay, distribution type 3, okay, usually refers to hurricanes, okay, coastal events, as well as essentially the monsoons that you actually see along the Pacific area. So again, okay, we really see, we do this within AGWA. You'll see this in several of the tutorials where we're going to use these design events to represent the rainfall input. So one thing I'll stress, okay, if you do not have actual rainfall data, you will never be able to capture the actual hydrographic shape coming out of a watershed. Okay, luckily for us, if we're using these models for planning purposes or essentially assessing the impact of disturbance, etc., we really can use a synthetic rainstorm event to look at cause and effect. All right, so in many cases, we can essentially do not actually use rainfall data. We'll use, okay, some of these design storms to look at the impact of disturbance or look at the impact of urbanization.
Just to add quickly that we do have multiple distributions built into AGWA now, and we have them built in with a map that shows where they're applicable. So when it comes time to entering a design storm, there's a little button that allows you to view a map of the different distributions so that you can select the distribution that's the most suitable for where your watershed is located.
Okay. All right. And then this is my last slide. Okay, channel parameterization. Again, we have hill slope elements and channel elements. All right. And you can come up with a unique representation for each channel reach. So you can change it with the depth relationship. We have within AGWA regional geomorphic relationships that you can actually use that covers the entire United States. We define the hydraulic conductivity of the channel it can go from 0 to higher values if you're seeing transmission losses. If you do not expect to have transmission losses, if you have a perennial stream, you want to set this to 0. Okay, but here in the Southwest, when you're dealing with intermittent or ephemeral channels, we usually have to set this to a higher infiltration value, hydraulic conductivity, to address these transmission losses. Roughness, okay, is it a highly rocky channel? Essentially, is it very wide, not very relatively shallow, rocky, has a high Manning's N number, okay, or basically is it more like a trench, okay, relatively narrow and deep, okay, then you'll have a essentially smaller roughness value. Since we can model channel erosion, you can adjust the erodibility of the channel, okay? Sometimes I do this because I'm only interested in routing the sediment that is coming off of the hill slopes, and I don't want to allow channel erosion. So I'll essentially highly armor my channel so I have no channel erosion and I can track sediment coming in from the upland areas. I'll talk more about this afternoon when we start talking about our management toolkit, but we can allow compound channels, okay? So we can actually have an overflow bank, for example. And again, each channel reach can have a unique set of parameters. It takes a lot of work to do this, but it is allowable. So you can actually come up with individual parameters for every channel reach. And if you're dealing with a perennial channel that you think you have groundwater input to that channel reach, you can set a base flow value for it. All right, so then you would be basically modeling runoff on top of the base flow. So that would be a constant that you would actually define. But again, you can have that constant, different constant for each channel reach. I think that's it.